Hello everyone. In this tutorial, we are gonna talk about how to zip large language models by using two different methods, quantization and offloading. I will provide the content as seen on the agenda. So we will first talk about why we need these optimization techniques. Basically, the large language models are huge, and how to zip large language models. We are gonna cover two important metrics: quantization and offloading. After that, we will apply a demo. We will run Mixtral-8x7B model on Google Colab. Large language models are huge in the sense that they require a lot of GPU, RAM. Here on that slide, you see several of the open large language models, and they are very huge. Actually, we mean that you cannot fit this open large language model into end users GPU. For example, the RTX 4090 has only 24 gigabytes of RAM, and this is the one of the most powerful GPU for the end users. So most of the open LLMs, they cannot fit into in that GPU just for inference. I'm not talking about the training or fine-tuning. First method is the quantization method. By using the quantization method, as seen on the slide, that Falcon 40 billion parameter model can decrease from 90 to 45 gigabyte. So it means that there is a half of the VRAM requirement is met by just quantization. And you see the other numbers on the slide. It means that quantization is an effective way of zipping large language models. I mean that the requirement of VRAM can be decreased when we use the quantization method. There are other examples for you. For GPT-3, Bloom, Llama 2, Falcon, MPT. In the community, there is a very famous guy, the blog. Here you see the blog. On the Hugging Face, the blog account shares the quantized version of the almost every version of the open large language models. Here is the blog account. On that account, every day, every hour, it published one quantized version of some LLMs. You see here that these are the recently quantized versions. So if an LLM just submitted 2 days ago, you can find the quantized version here. And actually, the blog submits a lot of information with the quantized version as well. Now let me go here and let me show you. Here is the Mixtral. For example, one version of the Mixtral, the size only 20 gigabyte for 3-bit quantization. And it's saying that very small high quality loss and maximum RAM required is around 22. So it means that it can fit into a RTX 4090. As you see that it supports how to install, how to run these quantized versions as well. So it's very good to know resource for you. Please note that this blog account on Hugging Face is very useful if you are interested in running some large language models on your local machine or on Colab, even for the free tier of the Colab version. Let's continue. Okay, after understanding the quantization works in reducing the requirement of VRAM, now let's get into the details of the quantization method. To understand how the quantization works, we need to understand or refresh our knowledge about large language models. So let's talk about the internal structure of large language models. You know that most of the large language models depends on the transformer architecture as seen on the right side. In the transformer architecture, actually we have the encoder and we have a decoder, as you see. And in that structure, we have substructures or layers. The first important layer is embedding layer. So its responsibility is to convert the text into some vector representation. And after that, we have a number of transformer blocks coming one after another. So you see here the one transformer block here in the encoder part, and you here see the decoder part transformer on the right side. Actually, a large language model has multiples of these. For example, 12 of these blocks are coming one after another. And the transformer blocks responsibility is to understand the content, understand the relationship between among the tokens, and create this relationship in terms of the vector representations. And another important layer is the dense layer. Dense layers are actually fully connected layers. They are just summarizing the data in one format or in one representation to another representation. It is mostly located inside some blocks, or they are located in between the two transformer blocks. But after all these layers and all these structures depends on actually some numbers. So these numbers are known as weights and biases. Of course, there are the filters and etc., but they are all can be thought as weight and biases. So as you see here, that is a simple neuron structure. So we have the weights for each connection coming to that neuron, and there is the summing function calculating a result. Then we have an activation function, change this result to an output. So all these actually are numbers, and the numbers in the large language models are represented as matrix or vectors or tensors. But all these tensors consist of numbers, and during training of a large language model, our aim is to find these numbers with optimum values actually. Here you see that all these layers can be represented as matrices, and all these matrices used in some calculations in matrix operations, and the input of the matrices are numbers. The matrices also have some other numbers, and the result of the operations are other numbers. So actually, when we talk about a large language model, when you download a large language model, actually you are downloading a big number of matrices. So if we have the number of matrices, we need to talk about how these numbers are represented in the computer environment, in RAM and hard disk. So as you know that in the computer design or architecture courses, the numbers are represented in different ways. But for the float numbers or the integer numbers, they are represented by the bits. Bits means that either 0 or 1 value. When 8 bits come together, it makes 1 byte. Almost. Most of the time, let me say. Okay, 1 byte actually can show, the 8 bits can show a number between 0 and 255 if it is unsigned. Alright. So we are just converting for example, decimal number to a float number by using a certain number of bits. So most of the time in the computer architecture, we use 32 bits representation for floating number, or 16-bit floating number representation. For the integers, you can use, for example, 8-bit, or of course 16-bit, or 32 bits. It's possible. So there are different numbers of representation for the numbers. But when you change the bits, I mean that from 32-bit representation to the 16-bit representation, what changes? First of all, the precision can change. The numbers after the decimal point can change. And the range of the numbers can be changed. So if you change the represented the numbers of the bits in the representation of the numbers. So the quantization all means that we would like to decrease the representation of the numbers in the sense of using bits. I will provide you several examples, but you need to keep in mind that our aim is to that weights and activation functions and the biases, all of them consist of numbers, and we would like to all the numbers are represented in the computer by using some number of bits, and in during training you can use 30 bits for training for representing a float number, for example, but in reducing the size of the VRAM requirement, you can change these ranges and reduce the range so that you can reduce the bits, so that you can reduce the total size. Let me go a little bit some examples. So how can it possible? For example, during the training you can use 30-bit floating point for your weights, but after that in the quantization you can change these numbers to 8-bit integers. For example, a weight value 0.456789 can be converted to 8-bit integer, the nearest one, between 0 and 255, potentially becomes 115. Of course, if you do apply all these conversion to all the existing weights and biases, then of course your large language model lose some accuracy and needs to be calibrated according to these new weights values, because the ranges changed and the precision changed from floating point to integer values. Therefore, you can use a small data set and to calibrate these weights and biases. After that, we can also apply the quantization in these 3 layers. I mean that we can apply the quantization steps: embedding layer, transformer block internal structure, and the dense layer. Or you can apply some of them 8-bit quantization, reduce to 8-bit, or some of the layers you can use 4-bit quantization. So there is a hybrid quantization methods as well. Let me go in another example for you. In that example, we will see a dense layer of quantization with very simple approach. Consider that a hypothetical dense layer with 10,000 neurons as the input and output is 500 neurons. So the weights will be 500, right? Because 1000 to 500 connections. And if they are all floating numbers, there will be each of them 32 bits. So 32 bit means that 4 bytes. So 4 bytes means that one weight will cost 4 bytes in memory. For the biases, there will be 500 floating point numbers, each of them 32 bits. Then 500 times 8 or 4 byte total memory. So each weight and bias are represented with 4 bytes for the moment. Let's continue with the example. So we would like to quantize this model to a 8-bit integer quantization model. What we can do? First, we can map each weight and bias values to 8-bit integer. It means that you are converting all the float numbers to map into the range of 0 and 255 as an integer. If 8-bit, you know that 8-bit is just 1 byte. Remember that in training we use 4 bytes for each weight and bias. Now we are using only 1 byte. Of course, we are losing a little bit accuracy. We will discuss this later. So after we apply the calibration so that we just arrange the ranges and the data. After that, let's check the storage. The weight and biases now occupy only 500 kilobytes and 500 bytes, weights and biases respectively. So it is means that for 4 times reduction and from 2 megabyte requirement. So it simply says that literally we are zipping the models matrices or the numbers, weight and biases. In the other advantage is that we can fit into a smaller GPU memory. Also, since we are using arithmetic integer values, the integer arithmetic is less costly compared to floating point operations in CPU and in GPU. So it means that our model inference time, running time will be improved a lot. Of course, we are losing a little bit accuracy or precision. Now let me continue for you with the third example. In that example, assume that our floating point weight matrix it's like that. So there are 4 inputs and 3 outputs. 4 by 3 tensor here, you see. And if you would like to convert these numbers to 8-bit integers, so it means that between 0 and 255 integer numbers. So what we are gonna do, step by step, we need to first determine range and scaling factor. So range means that what's the minimum number, what is the maximum number, and scaling factor means that we need to find a multiplier all the numbers such that they will be, after multiplied by that scaling factor, they will be between 0 and 255. Therefore, we do very simple mathematics like that, and we can calculate 135 as a scaling factor. After that, we need to center the values by just, from all the numbers, we just subtract the minimum value, as you see that, and then we find all the numbers as positive numbers. You see that the minimum number becomes 0, all other negative numbers becomes, and all of them becomes positive numbers. Since now we have positive numbers, we can just multiply by the scaling factor, so that the largest number, you see that here 1.8, very near to 255. Now notice that after mapping these 32-bit floating numbers to just a floating number between 0 and 255. As a last step now, we can just convert all these floating numbers to integer nearest integer number. And in the end, we begin with a 32-bit floating point representation of this weight matrix. Now the weight matrix becomes a matrix of integer numbers. The range of these integer numbers is now between 0 and 255. I think with this example, you would understand the quantization in simple terms. Okay. The benefits of the quantization, actually it's very clear, and we can already discuss it. But let me go over. First of all, we reduce the model size. We accelerate in the inference time because of removing the floating numbers and converting to the integer calculations, arithmetic. So we have the faster inference and lower energy consumption because of this faster inference. This is the result. So there are many benefits, but we know that there is no free lunch. So what is at the risk? Of course, the accuracy trade-offs. So quantization can introduce slight accuracy loss, but if you apply careful calibration and technique selection, you can just remove this risk or minimize this risk to a certain level. And there are some discussion about also hardware compatibility according to the underlying GPU architecture. Okay, there are several methods, there are several ways to apply quantization for a LLM, when you apply the quantization, actually you can apply the quantization on a trained model. So it's called post-training quantization. In the post-training quantization, you train a model, for example, with 32-bit floating point representation. When the training is finished, then you can apply this quantization. Then you have two versions of the model, one original, the other quantized version. And there are several methods: PTQ, NF4, QLOMP, let me say. These are the methods. So there are many libraries on GitHub. You can use these libraries. These are the example libraries from GitHub. The other one is other phase of using the quantization at training, during training time. So it's called quantization aware training, QAT. It means that during the quantization, during the training, you apply the quantization for the weights and biases at the same time. Actually, it's a very complicated approach. It can help, or it can reduce the training time to some level. But you need to be careful about this method when you use it carefully. So there are several libraries available, QAT, LLM QAT, and others. The third one is efficient fine-tuning with quantization. When we use this quantization method, as the name implies, when you need fine-tune a very large language model, you can use the quantization along with the fine-tuning, which can save memory a lot. And the famous one is LoRa, QLoRa, and you can find these libraries on GitHub. And there are other quantization methods as well. So let me show you some numbers again. Here are another table for some popular open source large language models, and you see that the VRAM reduction is very much. And I strongly suggest you be aware of this technology and use quantized methods using the Hugging Face, the blog account if necessary. So far we have covered the first three items of this tutorial. Before continuing with the offloading, let me remind you that Murat Karakaya Akademi YouTube requires your support kindly. In 2024, my goal is to reach 10K subscribers. Please help me on this. How can you support this channel? If you like the content, please first of all subscribe the channel. Thank you. Second thing, you can like the contents, and at least you can write some comments to the videos so that YouTube algorithm can take off the rest of the things, and so we can access many more AI enthusiasts. And I suggest you also please share Murat Karakaya Akademi YouTube channel link with your interested friends so that we can create a bigger community with your help. Thank you in advance. Okay, now we are gonna see the second method, offloading. In the offloading, actually, again, the idea is the same. During inference time, we would like to use not all the weights of all the layers and keep them in the GPU memory, but we would like to just slash the model into some layers, and whenever they are required, we upload these layers to GPU memory. So there are several ways to use it. I will go over the examples again with you. In here, Mixtral-8x7B model will be our main example in the demo. For the demo, actually, I will let me go over. I will use the Colab, and in the demo Colab, yes, it looks like it is running still. It's good. In the Colab, I provide the link in the video descriptions. Okay, I will explain this notebook in a moment. This notebook is shared by the authors of the paper that suggests how to use the offloading in the sparse mixture of experts approach. I will explain in a moment. Here, let me show the running requirement here now. You see that the GPU is only used 11 gigabyte GPU is used, and normally you cannot run this easily. It requires actually 120 gigabytes of RAM. But let me show you if it is working. Who is you? Let's see if it works. So if you check that now, this is 15 gigabytes is enough running this big model. Here it's beginning to answer. Yes, it is a little bit slow compared to GPT, of course, but it is just creating. And don't forget that normally Mixtral-8x7B model, I am sorry, 7x7B model, 8x7B model actually requires more than 120 gigabytes of RAM, but now it's running only 10% of this memory, and it looks like miracle. And it is just, yes, it's just creating a very long text, as you see. Yes, and still it's creating. So let me continue with the how it's possible. Let me continue with content. So offloading is a very simple idea actually, but the implementation is complex. The idea is that model sharding. Sharding means that actually you just use several layers, group several layers, put into some layers into shards. Shards means piece of layers, 3 layers, 4 layers, or blocks of the transformer blocks into a group. So after that, now we have the sharded LLM. So in that sharded LLM, as you see that these LLMs, these sharded parts of the LLMs can fit into your GPU RAM. After that, we just load these shards when they are necessary to upload. Why? Because as you know that in transformer architecture, it runs layer by layer. So each layer's output becomes another layer's input. Therefore, a couple of layers can be run together in the GPU RAM, and they can just produce the output. Then you copy the output. Then you just switch the sharded LLM. The next shard you can go and continue with this shard by providing the current output of the recent shard as an input to the current shard. So they can switch like that. That's the main idea. So you do the computation with the current shard, then you copy the results, then you offload the shard to the hard disk, and then you copy the next shard, and this way you can just in a cycle you just load, offload, load, offload. You are switching between the shards in an order so that you can just imitate that the whole model is running. Therefore, the offloading technique allows for the use of large language models even on a hardware with limited GPU memory, if this limited GPU memory supports some at least a shard of the large language model. So by using this you can fine tune the LLMs, large LLMs as well. So it's not only for inference, but this technique can be used for fine tuning as well. So some of the researchers already proposed many techniques, and these methods as a library, they exist on GitHub as well. You can download and use it easily. Today I am going to cover actually some libraries. So there are many, but the most popular ones, for example, DeepSeek. It's developed by Microsoft Research, and it can support several different ways of your model offloading. And Megatron also, it is developed by the NVIDIA, and you can download and use it for your requirements. Fair Scale from Facebook AI, and Hugging Face Transformers library. Actually, they can support deep speed and fair scale offloading. It means that by using Hugging Face interface, you can download any model and you can convert it to offloading version of it. So you can fine tune any Hugging Face model. It's good. Now today, actually, I am going to talk a very recent paper. This paper just published on 28th of December 2023. It means that almost 10 days ago. And the novelty in that paper is that they suggest an offloading strategy for mixture of experts. So far, the offloading methods only support the let's say popular transformer architecture, but a mixture of expert architecture is different than that generic transformer architecture, and this is the first paper supporting sparse mixture of experts. So how can you find these paper? Let me go and show you first. Just a moment. Okay. First of all, these guys, the authors of this paper, has a GitHub account. In that GitHub account, as you see that Mixtral offloading, you can just download this and run the demo. As you see here, I'm already running this here, and I will share the information again later on. And they have the paper, and I will go over the paper with you. So you can just follow these guys and start these guys. Let's start. So it's a very good thing that they do this, so that we can use it on Google freely, in the free tier of the Google, or you can download and you can run Mixtral on your local machine. At least you have 12 gigs of VRAM. Okay, let's continue. Let me continue with the paper. I will not go into the details of the paper, but I would like to share the important part of the paper. So the important part of the paper is that this offloading strategy or library is specially designed for this sparse mixture of experts model. I will not go into the details of the mixture of experts, but it's really important concept. If you are really interested in learning about that, let me know this. Please write into the comments section. So I would I would like to prepare a tutorial for you. So as they already expressed their ideas that this model is already designed for compress the model parameters and offload the parameters. So they also noticed the VRAM requirement of the large language models. So they are saying that RTX 380 or RTX 3060 can run after using offloading methods. So it's very good because they are affordable GPUs for almost anyone. So they are talking about mixture of experts and post-training and inference with offloading. So here again they are suggesting that we can use this technique. The Mixtral can run with a GPU 11 or 16 gigabyte RAM, as we seen on the Colab. It's real, 12 gigabyte is enough. So here they go into details of the how they implement this approach into sparse mixture of experts model. Basically the Mixtral 7x8 billion model using the open assistant dataset. So here they provide 4 different levels of quantization methods. So they use actually 2 things together, the quantization method and offloading together. And by using the quantization method, they show the how much gigabyte, how many gigabytes it requires after the quantization, and what is the result of that model with respect to some data sets, benchmark data sets. So here what is saying that these are the perplexity metric. So what they try to show that even using quantization and offloading, the accuracy of the or the perplexity of the model stays similar. The deterioration in the metric is negligible. And let me continue. Here what they show that the generation speed of the models by using the quantization and offloading, and as you see that it is almost 3 tokens per second. Yes, it is very slow, but at least it can work. So the paper goes like that. So for finishing, let me go back to this demo. In that demo, let me go over and explain a little bit. Okay, now these are the libraries that you need to just download, and then here are the common libraries. You see that Hugging Face transforms are used here. Then you just use a model from the Hugging Face, and then you can use the quantized version of it. Okay, and then after that, let me show. There is the offloading configuration. Since they provide a library, in that library you can configure these libraries parameters accordingly. And then here is the quantization configuration here. Then attention layer configuration. Feed forward network, it means the deep learn dense layer quantization. And all of them becomes the model quantization parameter. Then build the model according to quantization configuration and offload configuration. Then you build the model. Then by using the tokenizer from the Hugging Face, you just run the model in a loop so that we can just have the conversation as you see here. Let's say explain offloading. Let's check that if it knows, Mixtral knows what offloading is. I don't think so, because the training, let me see, known as offshoring or outsourcing. Of course, we didn't provide any context, so without the context, it thinks it's a general term in business operations. Yes. So as you see that it is generating maybe 2-3 seconds per second or more. Yes. But you please notice here that it is only 11 or 12 gigabyte of VRAM it consumes. It's very good because normally it consumes more than this. If you go to the Mixtral web page, they are suggesting more than 120 gigabytes of VRAM. But here we are just using only 10% of the requirement, and with still we are generating text. Where is it? It's here. I think it's a successful method, and thanks to the authors, we are able to run a very large language model in a very small, affordable setting. Here, as you see that only 12 gigabytes of RAM is enough. So at this point I conclude the tutorial here, but let me check if there is any question in the chat screen. Any questions? Murat Uçan, iyi akşamlar. Good nights. Ozay, good nights. If you have any questions, I would like to answer. If we don't have any questions, we can stop. Of course, you can write your questions after the live broadcasting under the comment section. I would be happy to answer your questions. Thank you for your patience and attention. Please do not forget to support the channel by just liking the videos and writing comments. Please take care. See you in another live broadcasting. Bye bye.